Hello, this is the Mr. Maths channel. Today is my birthday, and as a present to you all from me, which is pretty unconventional for a birthday, I'd like to go through a method that is more taught to you in A2, but is extremely useful for you to know in the lower six, which is AS. This involves complex numbers, clearly a concept that you should have covered by now and should be very, very confident with. But the method involves something called the Moivre's theorem, and you already have a sort of very basic introduction as to what de Moivre's theorem is. Even in the previous video with induction, I went through what de Moivre's might be, and I asked maybe as an exercise that you guys try and prove it. But that aside, if we have de Moivre's right here, just as a theorem, kind of going through it, we know that if we have some real number n and we have some complex number z, then z, if we define to be, I guess, anything that is relevant to our theorem, which is either the exponential form or the polar form. What you are going to be familiar with is the polar form, which is going to be r cos theta plus I sine theta. Then, what I'm going to do here is I'm actually just going to set r equals 1 because most of the times in the textbooks that you'll see with further maths, this is how your de Moivre's theorem is defined. If you have r equals 1, then z will just be cos theta plus I sine theta. The really elegant part of this theorem is the conclusion that you can reach based on a given condition. The condition is, suppose that n is real, then z to the power of n is just cos n theta plus I sine n theta. What this tells you actually is that if your r is 1, basically what you're just doing is you're rotating your complex number along some imaginary axis, which is really cool. Like, for example, if you have some complex number here, maybe with an argument theta, if you raise it to some power, then you're just multiplying theta onto it some number of times. Therefore, that's what your new argument becomes, which is really cool. The property comes from the fact that you have an imaginary axis and then a real axis, and ultimately you're quite literally just representing a rotation in this plane of real and imaginary numbers. So this in fact is one of my favorite properties in all of mathematics, really, to know that raising something or raising a complex number to the power of something, provided that the modulus is 1, then it would just be a rotation, which in itself is really interesting. I really suggest that you look into how this works, and also how you can derive maybe the exponential form using what is known as the Taylor series. Bit of an aside, but that in itself is also a very interesting branch of mathematics, or rather an interesting part of complex numbers. Obviously this is A2 content, but I also suggest that you push yourselves. Obviously you are further maths students, you should be already very familiar with this, but it's really good to just push yourselves and then never plateau, basically. This de Moivre's theorem you already have an introduction to. The interesting bit comes when you consider that because the condition on n is that it just needs to be real, you can then consider every single power of n for z to the n to work, even fractional powers. And what do you know from fractional powers? They are equivalent, or they're exactly identical to roots. So if I have z to the power of a half, okay, and let's say z equals 3 plus 4i, then what you have over here is just square root of 3 plus 4i. It's a pretty standard complex number that you want to reduce down, or you're rather asked to reduce down. But there are multiple ways in which you can approach this. First of all is obviously the sort of algebra heavy method where you go, let's say there's another complex number w, which is a plus bi, then you would just say w equals square root of z, and then if you square both sides you get w squared equals z, and then, you know, substitute in, which then you get, if you expand outwards you get this expression, and then you just have 3 plus 4i over here, ab equals 2, a squared minus b squared equals 3, and then it's just a case of solving simultaneous equations. All well, all good, but there is a more elegant way in which you can calculate not only square roots, but cube roots, fourth roots, fifth roots, and ultimately this is a sort of general method in which you can just apply de Moivre's theorem, and it will compute for you any root very, very quickly and very, very efficiently. For example, let's take z to the power of a half over here. Clearly, this is just 3 plus 4i in a plus bi form. But this form, okay, because we want to apply de Moivre's theorem, this form isn't useful to us at all. What we want to do is we want to put this in polar form. So z is clearly just going to be the, first of all, we're going to consider the modulus, which is going to be 5. And then we're going to consider the argument, which is going to be arctan 4 over 3. Just going to use my calculator over here. Usually, if you're going to have some interesting decimal for your angles, you should round it up, or sorry, you should round it to more decimal places than necessary, because ultimately it's better to be more accurate than less. So if we consider arctan 4 over 3, then we have 0.9273. Let's take it to 4 decimal places. So 5 cos 0.9273 plus I sine 0.9273. I've used radians over here, and you should too. Obviously nothing wrong with degrees, but for what's to come later on in your further mechanics, even in AS, and just later on in general, I think you should be very familiar with the idea of radians. Obviously nothing wrong with degrees, but it's just sort of my philosophy as what you should do. Anyways, we have this equation over here, or rather this equality, I should say, a little bit more formally. If we consider de Moivre's theorem, then z to the power of a half, which is just this whole expression, to the power of a half, then what you're just doing is you're square rooting 5, okay, because clearly in this case that we have over here, r equals 1, square rooting 1 doesn't give you anything that is interesting. It just gives you 1 for whatever valid square root that you have. But yeah, what the interesting bit over here is that you can apply de Moivre's theorem to this bracket over here, cos theta, which is 0.9273, plus I sine theta, again 0.9273. You can move this power down and multiply the angle. So if you have a half times 0.9273 plus I sine a half 0.9273, then what the idea over here is that you can just compute what the half of the angle is, and then happy days, that's your answer. Or rather, I should be a little bit more specific. That is one of your answers, because through what is known as the fundamental theorem of algebra, every single I guess it sort of does relate to the fundamental theorem of algebra, but every single square root has two possible answers. Same thing with cube roots, there's three possible answers. So if I have maybe like z cubed minus a equals 0, then there's going to be three roots to this equation. In the same way, if I have the square root of some value, then I'm always going to have two possible answers for that. So, computing this, what you'd get is just a half. So going downwards, it's just going to be 4, 6, 3, 5, 1, 5, and then plus I sine 0.463515. And that is quite literally one of your answers. But the other interesting thing is that your other answer is just going to be this plus pi. So what you're going to be considering is plus or minus this entire expression. And another answer that you could have is this plus pi. So that is a very, very fast way in which you can compute square roots, cube roots, fourth roots of any complex number that's given to you. And it doesn't need to be any sort of nice complex number either. It doesn't need to be 3 plus 4i. It doesn't need to be any sort of Pythagorean triple. This works for any complex number. Also, well, the nice thing about this is that you can get your answer in a plus bi form simply by inputting this into your calculator, and then that sort of gives you your answer where, if I recall correctly, the square root of 3 plus 4i has two solutions, or rather, hold on, it has 4 solutions, so plus or minus 2 plus I, if I remember correctly. Yeah. It should be this, 2 plus I or 2 minus I, something of that sort. But ultimately what you get from here are two solutions. So yeah, that covers the method. What I do suggest you do is practice this for thousands and thousands of problems until you are absolutely the fastest person with this method. It is, honestly, I guess the maths behind it, to understand it, is quite elegant, which in itself kind of justifies why I think you should learn this maths. But not only that, it is just another method under your belt which you can use to attack the maths problems that you face in the further maths exam, which in itself, again, a very, very useful habit to have, a very, very useful method to have alongside obviously your standard method, which is the, expansion and then equating real and imaginary parts. So yeah, I think that concludes it. Thank you for watching as always.